Aloha. Aloha. Aloha kako, which means welcome everyone. I would like to start off with a little bit of protocol, and I'm going to introduce Shelley Pelfrey, who's basically runs our administration at Keck. She's going to do a mele komo, which is a welcome. So traditionally in Hawaii, if you were to enter onto someone's property, you would go, "Hey, I'm here. Is it okay if I come in?" And this is the reply that you would get from the person who's hosting. So Shelley will do a mele komo. At the end, she'll do 2 claps, pa'i pa'i, and we'll all do it together with her. Okay? So Shelley? Nani. So you're officially welcomed into this space. My name is Rich Matsuda. I'm the interim director of Keck Observatory. It's really cool that we're here to celebrate 30 years of science, which I think Keck 1 went into science operations in the spring of 1993. And I joined Keck in the winter of 1993, December of 93. So in a couple months here, I'll make 30 years at Keck. And I've been privileged to be a part of seeing Keck come into its full scientific productivity over those years. And as you know, over the 30 years, Keck has become the most scientifically productive and impactful ground-based telescope in the world, which we're all really proud of. We have a really great night ahead. I'm really looking forward to Andrea's talk and want to get to that as quickly as possible, but I think that we really need to do some acknowledgments before we begin. And I'd like to start by acknowledging special guests here tonight, Jerry Nelson's son, daughter, and family. And we miss Jerry so much, but he's such a big part of making Keck Observatory possible. Would it be possible for you to wave or stand so that we can acknowledge you? So Jerry Nelson's family. Thank you so much again for being here to celebrate with us. You know, the 30 years of science wouldn't be possible without the astronomers. So all of you astronomers who are present here tonight, as well as those who are not here and those who came before, for the amazing discoveries and the great work. Among that, I would like to thank the Science Steering Committee members that are here who have advised us and pushed us to do great things at the observatory. And then we really enjoy putting on this annual Keck Science Meeting. So thank you to the Science Organizing Committee, especially the co-chairs, Ryan Charnock and Mike Brown, for organizing this year. Also want to recognize the funders and partners that have made it possible, especially the UC and Caltech partnership that has been the bedrock of the observatory. Mahalo to the CARA board and members who are here for guiding us, and the partnership for supporting our operations all these years. To the universities and institutions that have helped, that have been involved in partnering scientifically, as well as instrument development and technology development, keeping us at the leading edge. NASA, which became a partner in 1996, and then institutions like University of Hawaii, Swinburne, Yale, Notre Dame, Northwestern, ANU, and sorry if I've left anyone out. And of course, to the forward-looking foundations that have provided funding for the advancement of the technology at Keck. So the W.M. Keck Foundation, of course, for their transformational gift, as well as the National Science Foundation, Gordon and Betty Moore Foundation, Heising Simons Foundation, Mount Cuba Astronomical Foundation, as well as major private donors. I think we owe all of these institutions as well as funders a big round of applause as well. So thank you. Also want to recognize the staff. So there's 140 of us about that work at the observatory that all have a part in getting the telescopes on sky so that the astronomers can get their data. And not only those 140, but over the 30 years, so many that came before. Everyone plays a part, whether you're a staff astronomer, the vehicle mechanic, the electrician, the accountant, everyone helps in keeping us on sky every night. And I would like to recognize the staff. If you're a Keck staff member, could you please stand? Thank you so much. I would also like to single out a few staff members who put on tonight's Keck 30 celebration. Those three standing right there, actually. Megan, Shelley, and John. So thank you, folks. Okay, two more acknowledgments, and then we can get on with the show here. But I want to acknowledge Mauna Kea. So 30 years of science would not be possible without the privilege of us operating on the top of Mauna Kea. You know, it's clear, dark skies, high altitude, but also its significance beyond just astronomy. So culturally, ecologically, spiritually, to the Hawaiian people. I just want to remind us as we look up at the universe that we remember where our feet are planted. And that we are all grateful that we have a place on Mauna Kea, and that we should always be mindful of our impact to Mauna Kea and the people who hold Mauna Kea dear, and that we tread lightly. So mahalo e Mauna Kea. And then finally, the Hawaii community. So Waimea, Hawaii Island, all of the state of Hawaii. Waimea really welcomed Keck into the community. The owner at the time of the Parker Ranch, Richard Smart, gifted the land for the headquarters where we sit in Waimea. He felt that we would enrich the community, and so we try to uphold that responsibility and legacy of Richard Smart. And the communities around the island have embraced all of these employees that I'm talking about, and we also appreciate our collaborations with hundreds of contractors that help provide service to keep the operations going, as well as our collaborations with the State of Hawaii, University of Hawaii, and the other observatories on Mauna Kea. So those are my acknowledgments. Tonight we celebrate 30 years of amazing science. We have so much to be thankful for. Thank you for being here. It's going to be a great night, and I'm going to hand over to John so he can set the stage for Andrea.
So aloha, everyone. Thank you so very much for being with us tonight. I'm not going to say a whole heck of a lot about Keck Science and all the wonderful things that have happened in 30 years. In many ways, that's what the next couple of days are for. But I did want to highlight one aspect of it that I think everybody can personally connect with, which is why is Keck Science so impactful? And I think it has absolutely nothing to do with number of papers and number of citations to things. And I think it has absolutely everything to do with the personal connection that people have with the observatory. This is unlike any other observatory on the planet in terms of people's personal investment, the feeling that Keck is their observatory, the feeling that they are deeply connected to it in a way that goes beyond any individual night. And if I happen to be there, that's good because I always make the weather bad. But why is there that connection? So I'm gonna do a little fun audience participation. If you have been observing at Keck for over 25 years or more, or have been in some way participating with the observatory for over 25 years or more, please raise your hand. That's shocking, right? Keck is a wonderful facility in that it creates lifers. And what I mean by that is people who are dedicated lifelong throughout their research careers to both their science, but their community science, and also to the observatory, right? We have an amazing community of instrument builders. We have an amazing community of staff who facilitate the science. We have an amazing community of folks who help resource what we do at the observatory. And I think because we have a deep connection to the observatory, the science means more and has a broader grasp. And the other thing that we have is tenacity. when I look at what happens in Keck Science, it is a deep, long dedication to whatever it is, whether or not it's Andrew waiting how many years to get KPF built, whether or not it's Andy Skemmer convincing me to wait significantly less to get scales finished, right? Whether or not it's people who propose over and over and over and finally get their time and change the world. There's amazing ingenuity in our science community, but there's also amazing tenacity, and I think that's because of that personal connection to the observatory, which is why it's so great for me to be able to introduce Andrea tonight, because I think Andrea is the absolute embodiment of all of those things. Ingenuity, resolve, tenacity, and all of those other things. I could spend the next half hour reading Andrea's biography of accomplishments, but I think the most important thing about Andrea, aside from maybe this Nobel Prize thing you've heard about, is the commitment to bringing people to Keck, the commitment to bringing astronomy to the world, the commitment to bringing astronomy to young girls and women throughout the field, and really being a lifer in every sense of the word with the observatory. And so I don't want to spend any more time. I would rather that you spend some time listening to one of the greatest living scientists that has graced the observatory, Dr. Andrea Ghez.
Well, that was quite a setup. I'm really grateful for the opportunity to give this talk today. I'm really grateful for the opportunity to have worked at Keck Observatory for 30 years and to have worked on the top of Mauna Kea. I feel like my career is deeply intertwined with this observatory. When I was finishing grad school at Caltech, I saw the very first light images. And I knew at that point what I wanted more than anything else was to have a job that would give me access at UCLA. So I feel incredibly grateful that I do work at UCLA. I feel like I have my dream job. And it was part of an initiative at UCLA to begin an investment in infrared astronomy and astrophysics, in particular the technology and the methodologies associated with this emerging field. So I think it's important to say this project was not done alone. In fact, was started in 1994 officially, because that's the first year we put in a proposal. And what might surprise many of you was that it was actually turned down. It was turned down because people didn't believe that the technology that we were proposing to use would work. They didn't believe that we would see stars at the center of the galaxy, and they certainly didn't believe that they would move. So, in fact, yeah. Anyway, so that was an interesting start, and of course, it's really given meaning to my favorite expression in the world, which is every challenge is an opportunity. You just have to look pretty hard. And at that point, it was the opportunity to go up and down the UC system and give talks about what we had envisioned as a project. And it might surprise many of you to learn that this project was envisioned as a 3-year project, not a 30-year project. So this is, for me, very much a demonstration of what technology-driven discovery looks like, that every time we've made an advance in technology, there has been scientific payback, and in fact, more scientific potential. And that is still true today. Let me explicitly say who's in this picture. On the far left is Eric Becklin, who's here with us today. Mark Morris. So I think it's amazing that this collaboration has stayed together for 30 years. That's very, very unusual, and I'm really grateful for the collaborations I've had over the years, in particular with these two. And on the far right is my very first graduate student, Beth Klein. Many other people have been part of this in a really important way. So today we're a core group of about 24 people with a broader collaboration network of about 100 people. And let me in particular draw attention to Jessica Liu, who's on the far left, and then Tuan Do, who's just to the right of me. I often think of them as the new kids on the project, but they've been with us for, I don't know, at least 15 years. Jessica's here today. She can remind me exactly how long it's been, but it's so much fun because now, they were my grad students. Now they have grad students who are working on this project, and it's really fun in this multi-generational way. Now, the project started with a very simple question, which is there a supermassive black hole at the center of the galaxy? And that drove the initial work. And today, there's really two big picture perspectives on why studying the orbits at the center of the galaxy is an interesting thing to do. So initially, it was all about proving that supermassive black holes existed. But today, it's really about, from a physics perspective, understanding how gravity works in this extreme environment, the opportunity to test Einstein's theory of relativity in a regime that's relatively untested. From an astrophysics perspective, or an astronomy perspective, we're really after understanding what role black holes play in the formation and evolution of galaxies. And today, of course, we really understand that these two things are very, very coupled through this correlation. But in fact, when this project started, that was not the thinking. The thinking was which came first, the black hole or the galaxy. So it's sort of interesting how the whole context has evolved. But at the center of the galaxy, we have a really unique opportunity to see this feedback process in detail. Now, the Milky Way is the best place to address this question of is there a supermassive black hole at the center in galaxies, because it's the closest center of a galaxy that we'll ever have to study. It's 100 times closer than any other galaxy that we have to study. Now, like in life, for every pro, you usually get a con. So the pro is the proximity. The con, of course, is that we live in our galaxy, and to look through our galaxy, we suffer a tremendous amount of extinction, which of course makes it impossible to observe at optical wavelengths. But in the infrared, you can see some light, which is why this experiment is really deeply an infrared project. Now, orbits provide the best and most direct dynamical proof of the existence of a supermassive black hole. So in principle, what you're after is showing a lot of mass inside a very small volume. And specifically, you'd like to get down to scales that correspond to the Schwarzschild radius. And we're going to use stars as the test particles. And I like to say there's two techniques that we use. So the 3-year project was really after this first technique, which I used to call the inpatient or pre-10-year method, which is you want to measure the velocities. And initially, we were after velocities on the plane of the sky. And then as you go forward, you realize, or we realized, well, first that you could get accelerations, and then you could go beyond, because it was clear that the orbits were shorter than a human lifetime. So that was a really profound moment in this project when we understood that full individual orbits, which is a much more powerful way of getting to the proof of the black hole. For two important reasons. One is that since you're working on individual stars as opposed to ensemble averages, you get much closer, but you also eliminate all the assumptions that are embedded in these velocity dispersion techniques. Okay, so that's what we're after. And I think it's important to acknowledge the technology that was required to make this project possible. And one thing that's often not highlighted is the importance of the advances in infrared detectors. So in fact, just before this, the detectors simply weren't sensitive enough to do this project. So there's a timing both with the opening of Keck Observatory and the advances in infrared detectors. So they were now finally sensitive enough. Of course, you have Keck. But Keck alone isn't good enough. You actually have to have the technology that allows you to overcome the blurring effects of the Earth's atmosphere. So that's what had limited the work that came before us, and in particular the work that was done by Charlie Towns and his group up here at Berkeley. It's useful to recognize that, to get to orbits, it's all about the orbital period. And there's a very strong function of distance. And this is why this kind of measurement is only possible at the center of the galaxy. So you might do velocity dispersion and other work, but you're not going to get to the individual orbits, at least for the foreseeable future, because of that distance cubed factor. But 30 years ago, there were two groups who set off to do this kind of work, to figure out how to do high-resolution imaging work on the largest ground-based telescopes. So the first group was actually Reinhard Genzel, who started off with the NTT, so a 3-meter telescope in 1992. And then our group came in 1995 with the larger telescope. So then in the beginning, there was a little bit of baseline versus aperture size. But the two groups have been at this for the last 30 years. And I actually think from a point of view of the progress in science, it has been so wonderful to have these two groups. I mean, there's nothing like a little competition to keep you on your toes, but also because the other group is going to find all your mistakes. So over time, you know, there's been a lot of learning between the two groups. So people often ask, do we collaborate? Well, we don't quite collaborate, but there's a dialogue that goes on through your papers and through your presentations. And in fact, I think, and I've felt very strongly about this, that it's been important to have the independence of these two groups to really get the best thinking that we could possibly have around the center of the galaxy. Now, both groups started with the very simple technique of speckle imaging. And I think people might be surprised to realize that, in fact, it was the first decade that we used this technique. So a lot of this work was based on this very simple, what I like to call poor man's adaptive optics approach. So it just required changing the optics in front of the NERC, which was the original infrared camera, and then changing the electronics. So I think I was definitely a thorn in Hilton Lewis's side in his early career. So on the right, I'm just going to, sorry, on your left, you see the speckle images. So this is what very short exposure, a 1/10 of a second exposures look like. So it's freezing the interference patterns. And then speckle imaging is all about the deconvolution, so understanding what your atmosphere is doing to you versus what the underlying object is. And what is shown here is just the central arc second, 1 year, each year for that time period. And there's no cleaning up the image. I mean, I have to say, I love looking at this image. It's like old black and white videos from at least when I was a child. And you can probably find my favorite star in the universe. And its motion is not subtle. So you have to remember that people didn't think the technique would work and that we wouldn't see stars move. So seeing those first few images was just amazing, realizing that you don't need to look very hard to understand that there's something very interesting happening at the center of this image. Of course, technology advanced thanks to all the hard work of Peter Wazinowicz and his team, really making adaptive optics scientifically productive. And I say that because there was a 15-year period before Keck Observatory got its AO system going, where I worked with lots of teams, and we did a lot of engineering time and very little science. So Peter really created the first scientifically productive adaptive optics system, and he did this a decade before this was possible on the competing telescopes. Okay, so I'm not going to say much. Everybody knows how adaptive optics works. Lasers are pretty important. That's probably my favorite image of Keck, because we had telescope time on both telescopes, and it's like having two laser pointers saying, that's where the center of the galaxy is. So that's pretty fun. Okay, so adaptive optics was really powerful. Almost every way you can quantify the effectiveness of AO compared to speckle, it's about a factor of 10 better. And for the first time, you can do things at multiple wavelengths. So in speckle land, we're really only working at 2 microns in the K-band. And here we're starting now to work at multiple wavelengths. And really importantly, it's the first time that we can get spectra. And of course, spectra are so important for getting the third dimension of motion that we're missing from all the images. And what was really fun was actually figuring out the astrophysical nature of these stars that we were really just treating as test particles. And here there were just tons of surprises that were waiting for discovery. Okay, So SO2, my favorite star, is definitely dominating the knowledge of the central potential, because really this is like a freshman physics experiment. I mean, the technology is hard, but in fact, at these early days, the physics was actually quite simple. It's important because you have complete phase coverage, both in images. So the coding here is that stars are followed by a solid line if they've been measured with imaging, and they're followed, sorry, I did that wrong. They're followed by a dotted line when they only have imaging, and when you get the addition of the spectroscopy, you get followed by a solid line. So SO2 dominates, but there are a couple of other stars that are now short enough that we have complete orbital phase coverage and are starting to play really important supporting roles in what we're trying to do today. But not getting too far ahead of myself, at the outside of this experiment, it was really the work that was done by Charlie Towns, and we knew from him that there was 4 million times the mass of the sun inside an enormous region. It was basically a parsec. And you're 10 to the 4th times out from the Schwarzschild radius. So he doesn't suggest, in that paper, it's fantastic. You don't see it in the title, you don't see it in the abstract, but it is in the paper that it possibly could be a supermassive black hole. But today we can forward this because we've confined the mass to a volume that's 10 million times smaller. And that's hard to wrap your head around. So the thing I like to say is, imagine anything you would like more of. I don't know, your salary, lab space, I don't know. And multiply it by a factor of 10 million. Like, that's the advancement that has been made. And I should point out that the first step, the velocity dispersion, got us the first factor of 1,000. And then the orbits get you the next factor of 10,000 to get you to that 10 to the 7th. And it's amazing, like, to think, this project has shown that there's 4 million times the mass of the sun inside a scale that corresponds to our solar system at the center of our galaxy. So that's the big ta-ta. So today we have the strongest evidence to date for the existence of a supermassive black hole, and it's in our very backyard, even though it was the active galactic nuclei that made us think about the possibility of supermassive black holes. Okay, so now what? Now the work is no longer about proving that there's a supermassive black hole, but rather understanding the physics and the astrophysics. So let's start with the physics. So the first thing that becomes apparent is as you understand the geometry of the orbit, you can go after understanding how the gravitational terms. So and all the power, it turns, actually the exoplanet guys can tell you this, all the power comes from what's known as the turning points. The turning points from the point of view of the images, so the furthest and closest approach from the two-dimensional point of view, and the radial velocity turning points. And the radial velocity, actually I didn't put in the radial velocity measurements, but they're kind of amazing. They go from 4,000 kilometers per second to minus 2,000 kilometers per second in the space of a few months. And so that's why you can do RV work with OSIRIS, right? It's amazing. And once you get to the second time around to either turning point, you make an advance. So the first turning point that we got to see twice was the closest approach, and that happened in 2018. So for a long time, we were 2018 or bust. And it turns out there were 3 turning points that happened in the space of 6 months. And that allowed us to understand or to show that for the first time, you can't use Newtonian mechanics to model the orbit. And it beautifully fit the predictions for the gravitational redshift. So that was exciting and gratifying and confirms the theory. Now, it actually gets more fun when things don't work, actually, in my opinion. So now we're after the next turning point. So the orbit is 16 years. That means every 8 years you hit a turning point. So the next thing that we're after is the precession of the periapse. So that's like the precession of Mercury. And there's a very clear prediction from just gravity. So if it's all about the precession from gravity, you expect it to go prograde and at a very predictable rate. And what's exciting, from my perspective, is that the orbits are not conforming to this. They're actually, or SO2 is actually going at the opposite direction at twice the rate. Okay, so now what does that mean? Well, that means either you've made a mistake or you've made a discovery. And I actually think this is the most interesting part of research when you're not quite sure. Okay, so we, as many people in this room can tell you, especially Jessica, we have tried to find the mistake. And the dominant source of uncertainty for this measurement, it's all about how well you can define your astrometric reference frame. And if you had told me 30 years ago the topic I would be most interested in was the astrometric reference frame, I don't think I would have done this project. It's really hard because all your reference points are moving in a straight line, and in fact, they're all in the central potential, so they're all accelerating. So there's all sorts of interesting things that as you go further, you have to pay attention to, but we can't make it go away. I mean, we've really tried. Okay, so if we believe it, and remember, we're not quite at furthest approach yet. This signal is just going to get stronger as you go to furthest approach, which happens in 2026. This should keep giving us a signal. Okay, so what is the signal? You can replicate this retrograde motion with an extended mass distribution that is not luminous. So we'll call it dark, but we have to be careful because, of course, there are a lot of things. I don't necessarily mean dark matter in the particle sense. It could be dark matter in the sense of stellar remnants. And there's roughly just shy of 20,000 times the mass of the sun. And it turns out that's an interesting number. Okay, so let's just keep that in mind, that maybe we've discovered what's known as the dark cusp. Okay, why is that interesting? That's interesting when we start looking at the astrophysics. So this is an animation that I love. We're actually in the process of updating it. It was a collaboration with the University of Illinois' Advanced Visualization Lab. And they so thoughtfully coded so much science in this, and it's just pretty to look at. So the color of the star represents the spectral types. So there are stars that spectrally look young, and those are the aqua stars. And there are stars that look old. You can see their CO band heads, and those are the orange stars. And then there are things that we didn't even think to make predictions about, and those are the pink objects. Okay, so all three are inconsistent with the predictions of what you should see. So the predictions are you shouldn't see any young stars because the tidal forces are immense. So the densities of gas are pretty low. And it's not just a little problem in terms of the gas densities. The densities that you would need are 10 to the 11 times higher than what's seen today. So that's a big discrepancy. And yet we do see young stars. They're the dominant part of the population. Okay, so we've been calling this the paradox of youth for a long time. And as we continue to make measurements, you start to get orbits that are further well-known, that are further and further away from the black hole. And what was clear, and this is nice work that Jessica did as a graduate student, is that the planes of the young stars appear to align. And that was a really big hint and suggests that you might think of this as a scaled-up planetary system. And in fact, the ratios work really well. So maybe there was a pre-existing accretion disk, again, not so crazy, that these young stars condensed out of and form the young star population that we see today. Lots of challenges to this idea, because more than half of the stars aren't in the disk, so how do you get them out? Do you think of them as like an Oort cloud? And that remains a question today. The old stars are simply not there, and the old stars should have the distribution of a cusp. This is how we find black holes and other galaxies. You look for that concentration of light, and yet here, where we have clear evidence of a black hole, those old stars, which have had the time to form the cusp, are simply not there. And that's where I think this dark matter cusp is really interesting, because you can ask, well, how much mass is missing from the luminous cusp inside SO2's orbit? And the answer is about 20,000 solar masses. So that's when you go, oh, well, maybe not a mistake, and actually makes sense. Okay, so lots to do. Oh, and I should mention the pink stars. Okay, so the pink stars are really interesting. The pink stars are these stars that you can watch become tidally distorted as they make their closest approach. They're incredibly eccentric, like 0.99 something. And therefore, you see the evolution. You see them come in as compact objects and then pull apart, both at 3 microns and spectroscopically in the gas. And then they go through closest approach, and they become compact again. They survive. And so that was a big clue to us. And we actually think that that comes from black holes driving binary stars to merge, and when stars merge, they become inflated and big enough to have those tidal interactions, because you need stars that are about 100 times bigger than the typical stars to have that interaction. Okay, so that's fun and might connect with LIGO. Okay, so lots of science and lots of fun. Okay, now I'm going to make one left-hand turn. I'm going to do 2 left-hand turns here, because I thought, I'm going to say, okay, science has been really fun, but I wanted to save a little time to tell you about the Nobel Prize. The Nobel Prize for us came in 2020, and this was a really interesting year if you think about October 2020. So I still have a landline, God knows why, but it rang at 2 in the morning. And of course, my first thought was, oh my goodness, somebody's sick or dead. And then I quickly figured out that that was not the phone call I was getting, and that I was receiving the Nobel Prize. And I was invited then to participate in the press conference. And this is an interesting moment. So you're told basically, why don't you take a few moments to think about what you want to say and don't want to say to the media. You think, I'm tired. I haven't wrapped my head around winning, never mind how I talk to the media. But it was a really important moment for me, because the first question that got asked was, how do you feel about winning the Nobel Prize at a moment when science is increasingly under attack, and yet it's increasingly important because of COVID and we need a vaccine? That was the first question. So I think I learned a very important message at that moment, which is the Nobel Prize comes with a lot of opportunity, but a lot of responsibility. So it's been an interesting 3 years of trying to figure out how to interface with that responsibility piece. Now, people have often asked, am I disappointed to get a Nobel Prize during COVID because I missed the ceremony? And I think, how could you be disappointed to get a Nobel Prize? Like, it just doesn't make any sense to me. And I'd also say that it was actually really wonderful to have good news to share at such a awful moment. And in fact, that's how I thought about it. And it was a wonderful, oh yeah, this is my Nobel Prize ceremony. So it was interesting because they said, well, we're not going to have a ceremony in Stockholm. And then it was like, well, maybe we'll have it in DC for the US folks. And then it was, well, maybe the California people will go up to San Francisco. And really what they want is it filmed so that on December 10th, they can have video to stream out to the world about this prize. Well, California went into lockdown the Friday before the Tuesday that we were supposed to do this. So there was a really interesting weekend of like thinking, well, how are we going to do this? And I have to say, there was a wonderful opportunity or moment of community for me where I called a friend who was the dean of the law school, and she said, well, let's just read the order. She's like, well, there's an exception for film. So then it was like, who do we know in the film industry? So I start calling the film, anybody I know. And fortunately, I have kids. And the great thing about having kids in school in LA is that there are a lot of industry people in the schools. So my kids were like, oh, this person's parent is a big one. So we actually got a film permit pulled over the weekend so that we could actually do this in a lovely backyard of the couple that actually sponsors the endowed chair that I hold. This is somebody who came from the Swedish embassy. And one of the funniest moments, actually, I should have put this in. My favorite picture from this whole thing is that he's reading this along, and there's a film crew there, and a photographer, and my 2 kids. That's all that was allowed. And he gets to a point, and I'm thinking, that's not my citation. So I'm thinking, should I interrupt him or not? So I let him go through, and then I let him know, and there's this moment of just hilarious laughing that got captured, my favorite picture. So we had to do it again. So that's what actually got streamed. In December 2022, they actually had their first in-person ceremony, and they invited the previous 2 years to participate. So this is what the ceremony looks like for the 2023 guys, and then the two rows behind them are the 2020 and the 2021 laureates. I think they did a phenomenal job of curating this week to really honor the 2022 laureates while letting the rest of us participate in the adventure of Nobel Week. And I really didn't understand what I had missed. People said, "What, did you miss it?" I was like, no. But it was an amazing week. It's an amazing week because Stockholm gets so excited about this week. There's an energy in the city that, to me, reminds me of the Oscars. You go to the hotel, and there are people standing there wanting your autograph, and you think, really? But that's the way the city works. And the Nobel Foundation has you do an incredible amount of public engagement. So the first half of the week is all about sending the laureates out into the high schools, into the colleges, into the community, doing podcasts. You are worked from the first moment you wake up till you go to bed to earn that end of the week banquet. Another fun thing that happens there is that you get to contribute an artifact to the Nobel Museum. And so the artifact, and then they film it and record it about you donating it. And what I decided to donate was the first tape of our 1995 data and the first log sheet where we actually got data, okay? And data, to me, these days is such a big thing because it turns out it's really hard to keep 30 years of data accessible, alive, to understand all the data products. We are now collaborating with people from information science to figure out how it is that we've done what we do and how to keep doing it. My favorite part of the log sheet, if you ever go see it, is the first frame. We couldn't believe how good the seeing was. Now this is, and you'll hear from Eric, this is the data that was scientifically productive, okay? There was a different story for the first attempt. I got my 15 seconds of fame, or my King and I moment. I had an opportunity to sit next to the King of Sweden. Turns out he's been to 50 banquets. So I asked him, well, what was the most interesting banquet that you've been to? And he was so politic. He said, why this one? It's the first, it's the first time I've been seated between two female laureates. It's usually the wives. I thought, okay, well done. I think I got my best holiday photo ever with my two sons. And of course, it was really remarkable to be there with some members of the team. Not everyone was able to make it, but that was particularly meaningful. Now, because there are so many people, I decided to do something I've never tried before. In 2000, actually June of 2000, the Galactic Center group, in our collaboration, was celebrating our 25th anniversary. And we meant to do an in-person thing, but in June, of course, that wasn't possible. So we did an online thing. And a friend of mine suggested that we do a video interviewing people, just select people, that have participated or been part of this incredible adventure over the last, well, at the time it was the last 25 years. So I'm just going to play it. I might cry because I do pretty much every time I see it. It's really touching.
The first night that we really got good data, and we all knew that we had something really special there, come with the observations.
Persisting. I think I'm most proud of persisting. Well, I think my whole professional career has been defined by this project. It was a project that I didn't anticipate to be going on for 25 years. I think I envisioned it initially as a project that would go on for 3 years. And I had no idea what an adventure this whole thing would be.
But it was in 1994, and I think I was there because I remember seeing this awfully big image that filled the NERC small field of view of IRS 16. And that was the worst scene I'd ever seen at Mauna Kea. I've never seen it like that before.
I remember when we took home that first set of data, and I wrote the shift and add algorithms, and we didn't know what was going to come out because, you know, it's all just a bunch of spots on thousands of frames of spots.
I remember that. I do remember that. I remember the seeing was awful, and you had to wait 10 seconds for every exposure. It was most inefficient, but it told you that you could do it.
1% of the time was an exposure.
And you were destroyed. Keith said, "Oh, this won't work," and I knew it would because this was not a typical night on Mauna Kea, and I don't believe we've seen a night ever that bad since that one first image. You would remember that.
I'll never forget that afternoon, late afternoon. It felt like the department was empty. I thought I was there by myself, but suddenly got the whole thing to work, adding them all together, and this incredible map with all these sources just appeared on my screen. And I think Eric Becklin happened to be right there or something at the time, and he and I just were screaming over how cool that was.
I think my quintessential memory is trying to convince the telescope operator to remove the outer ring of mirror segments to observe at shorter wavelengths better in the less is more school of thought, or really to remove biases in the measurement. So what was your greatest challenge in working with this program?
I'm not going to answer that one completely honestly, but my greatest challenge, I think, was actually also the source of the greatest excitement. You know, every time it was an experiment. Every time there was something new, and we had to push the equipment and the capabilities we had way beyond anything that was ever imagined or designed for.
I still remember, as you perfectly know, sometimes it just can be damn quiet, right? And so we tried to sit there and catch a beautiful flare, but nothing was happening. And I still remember at some point we all got up and started singing, "Twinkle, twinkle, such a star, how I wonder what you are."
Leo and Mark Morris decided to sing "Twinkle, Twinkle, Sag a Star."
When we were in the Keck 2 control room singing "Twinkle, Twinkle, Little Star." That was seared into my memory.
Is it getting brighter today?
Come on.
Eric, this
Come on, Leo.
Okay,
I'll sing it with you.
Do it.
Okay.
Twinkle, twinkle, Saturday star, how we wonder what you are. Up above the world so high, like a diamond in the sky. Twinkle, twinkle, Saturday star, show us just how bright you are.
And this was it was very silly, but it was just so much fun to have all this frustration of Sagittarius Star not showing its brightest side, to put it in one song and try to sing it to life.
Well, when I look back on the research I've done in my life, this is probably the top of the list, the most exciting and the most fundamentally important research. So it means a tremendous amount to me in putting the ensemble of my life's work together.
I think, the change in our understanding of the galaxy itself. I mean, black holes were the things of science fiction. The theorists had postulated them, and there were indications of possibilities. But you know, the giant black hole at the center of the galaxy was not something I think that in 1995 or 1993 we were even considering as a possibility.
I don't remember the exact detail, but being shown that first animation and going, wow. I mean, that's where I use the word slingshot. A giant gravitational slingshot. I thought, there I am, looking at the universe do its thing.
Sorry, I should have prepared better. I guess let's say the thing I'm most proud of are the students. I feel so privileged to have been working with such an amazing team, and it's so much fun to see these students come through and go on with their own careers. I think, I guess I said two things, but those are the things I'm most proud of.
Well, but I think being part of this group has been tremendously important for my professional development and my work as a scientist, right? So having, done my PhD in the group, I really got a really good sense of how to pursue science in a really methodical and really driven way. And it's taught me a lot of patience, definitely, as astrometry is not a short-term game. But it also shows how tremendously rewarding it can be if you do persist through it.
I think my first memory of observing was out on the Big Island of Hawaii at Keck Observatory, and for sure Keith Matthews was there. That's what I remember, because I remember going to coffee with Keith, and I can't remember if Eric was there, but with Keith and Andrea for sure, and just hearing the scientific debate going back and forth. And as a young graduate student, being exposed to how you can have conflicting opinions and intense discussions and yet still be completely collaborative at the same time.
What are you most proud of in terms of your work with this project?
Is it fair to turn the question and ask you what you're most proud of me for?
And I had the opportunity to first meet you when you were an undergrad in Introduction to Astronomy and Astrophysics. And you wanted a position in the group. And you persisted. You kept coming back.
Yeah, that makes it easy. So the thing I'm most proud of is just being persistent.
You felt like you were part of science happening. I know that sounds very, very, sounds a bit trite the way it's phrased, but when you in class, you learn about discoveries by Faraday and so forth, and you think about just the experience that they must have had uncovering those things for the first time. Peeling back the onion, layers of the onion, on the cosmos, and that's always how I felt, about this work.
I think the work surrounding the supermassive black hole really shows that we're capable of making progress in an absolute sense. We start with intellectual endeavors, and at the end of the day we can actually demonstrate real physics. So I think in itself it shows the spirit and adventure of science, and it shows the power of the scientific method, and I think it is also inspirational, and that in fact is in the end perhaps the more important part.
Okay, we're going bigger. What does it mean for humanity?
Oh my goodness.
For humanity, it probably means what the whole history of astrophysics teaches humanity, and that is just the fundamental lesson of humility.
As you understand that bigger picture, you understand where humanity has a perspective of where it fits into a bigger picture. And so I think that's really the impact of the work.
Well, humanity's so stuck in its small-mindedness sometimes We can all be small-minded and forget about the bigger picture and get locked into the problems of the day. And, you know, we're all on the same lifeboat, the same blue, dot in the sky. And I think astronomy does this. It does uplift a lot of people, makes them feel small, but also makes them feel part of a much bigger picture.
It inspires people to, push science forward. So it gives us reason to learn more and to understand our world better.
And if you are at all conscious as a human being of the heavens and our place in them, it really opened up horizons that none of us, layperson or astronomer, had ever considered possible. So I think it adds to the wonderment of what is out there and what we little tiny specks of sand on this little planet can do. It's really amazing.
It stirs us philosophically at our deepest roots.
I think this is something we teach when we teach those introductory astronomy classes. But science sort of started with astronomy. How people started looking up the sky and then wondering what's going on up there. So I think it's just driving curiosity.
This is a treasure, and a growing treasure. It gets more and more valuable every time we look at it from a slightly different perspective.
For humanity, it just shows that there's so much out there that we really don't know about. And we, the little quibbles that we have here on Earth are really that, just little quibbles relative to what's really going on out there.
Well, fundamentally what we're doing is we're serving humanity's curiosity. It goes back to Galileo and the what is the center of the universe? Is it us? Is it the sun? Is it the galaxy? I think we're doing something very fundamental for humans.
So what do you think this project means for humanity?
Squat. Not very much.
That is the answer I would have expected.
Well, this has been a good way to top off my my scientific career, being involved with this project. It's just been one success after another, and I've just been blessed and honored to be a member of it.
That makes two of us for sure, Eric.
So, the thing I love about that is we did it 4 months before Nobel. So that was really from an authentic perspective. And the guy who did it had me ask the same 10 questions of everyone, and not questions I was comfortable asking. But it was really fun. I'm really glad we have this as something to hang on to going forward. And I think we have so much more to do. I mean, the technology that's still advancing with Kappa and Liger and scales, there's just so much more. So let me end by saying happy birthday, Keck Observatory, and we really look forward to the next decade of discovery. Thank you.
So a couple of quick things. First of all, Andrea will be signing autographs in a reception line. Okay. And at risk of making one more joke, I'm really thrilled to have you all here celebrating 30 years of squat and humanity's quest thereof. No, I have not seen this video before. It's wonderful, and I think it does speak to a much, much larger thing, which is just this community and spirit of excitement in science and just our understanding that it creates. So please join me one more time in thanking Andrea for what a wonderful presentation.